Okay, first we're going to start out with the last example from 8.2 as your warm-up. So the video is going to pause. I'm going to ask you to solve this, and then we'll check your answer together. We can find h and k. The bigger denominator gives us a, smaller denominator gives us b. Pythagorean relation gives us c, but we do need to simplify that radical. The center is hk. The vertices, we start at the center and go up and down by a distance of a. For the foci, starting at the center, go up and down by a distance of c. In the graph, the way we see b is our minor axis, so that's side to side from the center, a distance of b. For the summary and reflection, what I'd like you to do is think about what are some similarities and differences between parabolas and ellipses, either in the way that we sketch them, in their properties, the variables we solve, or in their standard form equations. Add those to your summary and reflection, and then we'll take a look at our new section from section 3, which is hyperbolas. For section 3, we're looking at hyperbolas. Hyperbola is the only conic section that crosses both napes of our cone. So if we're looking at a cone, a hyperbola cuts through both parts, meaning that we're going to have a discontinuity for when we cut through the space between the two napes. So a hyperbola, a slice of both napes, will look like this. Now we've seen a hyperbola before. Remember, y equals 1 over x is a hyperbola, but we are going to be looking at the quadratic form of a hyperbola. And if you look at our kind of most basic standard form equation, where h and k are both 0, you might notice that the big difference between a hyperbola and ellipse is that hyperbola is subtraction. So we'll make this same kind of rectangle with our a and b values, but instead of sketching the ellipse on the inside of that rectangle is going to give us the asymptotes that our hyperbola follows. So we will still have 2 vertices at the end of our a values. We will still have 2 foci measured by c. So let me draw a sideways opening hyperbola. We will have a center. At a distance of a, we will still have 2 vertices. At a distance of c, we will still have 2 foci. But when we measure our distance of b, it no longer gives us a point on our conic section. What that's going to give us is the slope of our asymptotes. Every hyperbola has 2 asymptotes, and the slope is rise over run. So in this case, we could say rise b run a. So this would be a slope of b over a. And this asymptote would have rise b run negative a slope of negative b over a. So the big differences here are that it's subtraction, which is called a difference. And also now our focus is further away from the center than the vertex. So C is greater than A. Those are the 2 main differences between a hyperbola and an ellipse. So let's take a look at our chart. Okay, so in this diagram, we said from the center to the vertex is a distance of A. From a center to a focus is a distance of C. From the center perpendicular to those measurements is a measurement of B. Now that measurement of B is just to find the asymptotes. So we can take that measurement of B in both directions, make this rectangle similar to what we did for our ellipse, except now that's just going to give us the slope of our asymptotes. Now, since the coordinate for the center is hk, we can find the equation of those asymptotes using y minus y1 equals m times x minus x1, where our point x1, y1 is the center hk. Both asymptotes go through the center. And the slope, like we were seeing in our last example, the slope would be b over a and also negative b over a for a horizontally opening hyperbola. So what we end up with is the equation of the asymptote y equals plus or minus b over a times the quantity of x minus h plus k, where a, instead of being called the semi-major axis, is now called the semi-transverse axis. So compared to the major axis, now this is called the semi-transverse axis. So the whole transverse axis will be 2a. The transverse axis goes between vertex to vertex, just like the major axis. We can't call it the major axis anymore because what can happen is that our a value can actually be smaller than our b value now. C will always be greater than a, but a will not always be greater than b. So we have new names. The semi-transverse axis goes from vertex to vertex. The semi-conjugate axis is what we're calling the new minor axis. But again, it's not always going to be smaller than A, so we don't want to call it the minor axis. So what this does is it goes with a length of 2b between the two halves of the hyperbola. So the transverse, think about like the transatlantic trade went across the Atlantic, transcontinental railroad went across the continent. So the transverse axis goes across the two halves of the hyperbola. Conjugate is when we compare, for example, a plus b to a minus b. So we're comparing two things, we're looking between them. And so the conjugate axis goes between the two halves of my hyperbola. And its entire length, conjugate axis, is 2b. Okay, so now since C is our longest distance from the center, we have a new triangle here with a side length B and A hypotenuse of C, which means that our Pythagorean relation is actually the Pythagorean identity, where C squared is A squared plus B squared. Okay. Our standard form of the equation, just like we saw on the 8.3 packet, is going to be almost identical to the ellipse, except with subtraction. So we start with x minus h squared over a squared, now minus y minus k squared over b squared, and still equal to 1. Okay, now because this is subtraction, these are not commutative. So a doesn't always have to be bigger than b, but it will always be the positive factor. And then b will always be attached to the negative fraction. Our focal axis for a sideways opening hyperbola, we have two foci, two vertices, and the center. So this is going to be a horizontal line, y equals k, which means all of our points have a y value of k, which means it's our x coordinates that are changing, for the foci changing by a value of c. So that's going to be h plus or minus c, comma k. For the vertices changing by a value of a. So that's h plus or minus a, comma k. We can do the same thing for an up and down opening hyperbola. So that means the roles of x and y change. So we have y minus k squared over a squared minus x minus h squared over b squared equals 1. Notice a squared is first, but also attached to the positive fraction again. B squared is negative. So the negative always goes with the b squared. The term that has the a squared, the first one, is always positive. This is an up and down opening hyperbola, so all of our critical points line up vertically at the equation x equals h, which means all of our critical points have an x value of h. Then our k value changes by c for foci and a for vertices. The last thing is for a vertically opening hyperbola. Let me make sure this stays on screen. For a vertically opening hyperbola, now our a value is up and down and our b value goes out to the side. So our slope, our rise over run for our asymptotes will be plus or minus a over b. Now the roles of a and b changed, and also the values of a and b changed. But the rest of the formula for this asymptote is the same. So the only difference between the equations of these asymptotes is the reciprocation of the slope, okay? Now you don't need to use this formula, just like for the other two charts. This is to help you get started, but the goal is to be using these relationship values of A, B, and C in order to solve these conic sections without needing the chart. So the goal is to be able to solve them without the chart, but you can use the chart to help get you started. Okay, let's look at some examples. Before we jump in with example 1, in the section 3 notes, there's a little gap above section or example 1. I want to draw in our axes and remind you how to draw that rectangle with A and B because we're going to be using it a lot. So I'm going to do a sideways opening hyperbola. The vertices are on the hyperbola. The foci are inside of each of those arms. Looks kind of like two parabolas. And then we have the center. We have from vertex to vertex, going sideways. For this is our transverse axis, which means at a distance of A on each side and a distance of B going up and down, we get our conjugate axis with a length of 2b. I put these as arrows. They really should be endpoints. We have our conjugate axis. If I connect the values of A and B into a rectangle, that is how we get the asymptotes through the corners of each of the rectangles through the center of the hyperbola, always through HK. And then we can see that C is here our hypotenuse, but also the distance from the center to the foci. Each focus is a distance C from the center. Okay, so in example 1, we have an equation here. We want to find the vertices and foci. For the vertices, I need to use A. For the foci, I will need C. And we have this equation. Well, it's not in standard form because this is not equal to 1. So we need to fix that first, divide everything by 36. Now this should feel familiar. We did very similar problems when we did the ellipses because I want you to be able to see the comparison and the differences between the calculations and the results for ellipses and hyperbolas with the same values for A and B, H and K. Okay, so here we get x squared over 9 minus y squared over 4 equals 1. Now it's in standard form. Think about this as comparing 9 to -4. The first one will always be bigger. So a squared is 9, a is 3, b squared is 4. The negative is not part of the b squared, right? It's minus and then y over b squared. So the negative is not part of our value for b, which is 2. Now we need c because we need to solve for the foci. So we need to use the Pythagorean relation, different than the ellipse. C squared is a squared plus b squared. I have a and b, so I can solve this. 9 plus 4 is 13. So c is the square root of 13. We're only interested in the positive value because we're looking at c as a distance from the center. Okay. Lastly, we need h and k. Since I see no numbers are subtracted to x or y, that's also being squared. So there's no numbers with x being squared and no numbers with y that's being squared. I know that h is 0 and k is 0. So that tells me that the center is 0, 0. Since x is first, I know this is opening horizontally. Going a distance of 3, I get my vertices. Perpendicular to that, I go a distance of 2. That makes my asymptote rectangle. So here are my asymptotes. The vertices are actually on my hyperbola. So I can say here is my hyperbola. Okay. What we're missing on this graph is C for my foci. Well, the square root of 13 is a little bit more than 3, but less than 4. So my foci are inside of each part of my hyperbola, but further away from the center than my vertices. The graph does not go through the foci. So the vertices, that's these 2 points that the graph actually goes through. If you look on the graph, the vertices are at positive and negative 3, 0. And the foci, the points that the graph does not go through, are at plus or minus square root of 13, 0. I want you to think about and hypothesize what would change if the equation with the same coefficients of x and y just switched. So y is now positive and x is now negative. What do you think would happen? Now let's take a look. We still have to divide everything by 36. Y squared over 4 minus x squared over 9 equals 1. Now 4 is bigger than negative 9. So a squared is 4, a is 2, b squared is 9, b is 3. Now, a squared is underneath my y is the positive. So this is going to be an up and down opening hyperbola. I'm going to use a second color here to show that the distance 2 from the center to still gives me the same distance to the box that I used before, the rectangle, and B3 gives me the same distance to that rectangle. So the rectangle is actually not going to change, which means that the asymptotes don't change. Now, the reason this happens is because even though A and B switched values, they also switched directions. So it's going to have the same rise over run, and it's going through the same center. What does change is that these points are now vertices. And so my hyperbola, opening up and downwards, still goes along the same asymptotes, but now it goes through different points. Okay. Important to note here also, because A and B changed, but they just switched values, our C is still the square root of 13, which was a little bit more than 3, between 3 and 4. So if I graph that, my foci are still 1, 2, 3 inside of my hyperbola, further away from the center, but kind of surrounded by the arms of my hyperbola. Okay, go ahead and pause if you need a little bit more time with this. we're going to look at example 2. We want to find the equation of the hyperbola with foci 0, -3, and 0, 3. Remember foci. So from here, we should be able to get the variable c. And then we also know that the conjugate axis, we should think minor. So think minor axis, which tells us that the variable involved is b, has a length of 4. So 4 is 2b, b is 2. And then we know we can get c here if we graph 0, -3, and 0, 3. We can get the center. Center is halfway between. So in this case, the center would be 0, 0. So far, none of these points are actually on the hyperbola, right? The foci and the center are important critical points, but not on the hyperbola. Now we know that the hyperbola should go around the foci. So since these points are vertical, up and down from each other, we know that our hyperbola will open up and down. If the center is 0, 0, then the distance here, a distance of 3, is our c value. C is 3. Then all we're missing now is A. H and K are given from the center. H is 0, K is 0. So to find A, we're going to use our Pythagorean relation. Now remember, C is our largest distance now. So C squared is A squared plus B squared. C squared, sorry, we know C. So 9 equals A squared plus 4. 5 is A squared. Then A is the square root of 5. So now we have A, B, C, H, and K. We can find our equation. We need to know which variable is going to go first, X or Y. Because this is opening up and down, it is our Y that goes first. So this becomes Y minus K squared over A squared minus X minus H squared over B squared always equals 1. I know that my K value is 0 and my H value is 0. So I have a Y squared over something minus X squared over something equals 1. And the last thing is our denominators. Make sure that you're doing A squared, which is 5, and B squared, which is 4. For example 3, I want you to try that on your own. Feel free to ask classmates if you have questions. Work together on that, and then we'll go through the answer together. So we have, we're finding the standard form of the equation of the hyperbola whose transverse axis, think major axis, has the endpoints here given -2, 1, 8, 1, and whose conjugate axis, think minor, has a length of 8. So that means that 8 is 2b, b is 4. We can say these 2 points are a certain distance apart, and if you count or subtract, that distance is 10 units apart. So we can find that our center halfway between is at 3, 1, giving us H and K. We have H, K, B. Well, if these two are the endpoints to our transverse axis, then they are also called vertices. Vertices. And therefore, we know that the distance from the center to each vertex is A. So we know also that A is 5. Now we could find C, but just to find the equation, we don't actually need C. So you can save yourself a little bit of time by saying, okay, I need to know which way this is opening. If these are my vertices, then it must be opening sideways. Let's go ahead and sketch what this would look like. So B is 4, 2, 4. 2, 4. So I'm making my A, B box. So this is B of 4, A of 5, which means here are my asymptotes. And here is my graph. If it's opening sideways, then we know that X must be our first variable, X minus H squared over A squared minus Y minus K squared over B squared equals 1. H is 3, A is 5, minus K is 1, B is 4. And so that is our equation. Okay. If you have time left during class, you can use that to start the Math Excel. Otherwise, if you're finishing this for homework, then the rest of your homework is the Math Excel. There will be a homework quiz next class, and then we'll do the last example as the warm-up, and the rest of the back of the page is for kind of reviewing and going through the chapter before the chapter test.